All right. Well, thank you very much for the introduction to speak to everyone today. I know that perhaps I don't have the current background that you would expect to hear for an astronomy magazine, but I do have some experience in space, and I would like to draw some parallels to work that has been done in space regarding mechatronics and robotics. Also to explain more in detail what we're doing at CERN right now with mechatronics and robotics, and we can see where the challenges are similar and where they're different. Okay, so I'm working at CERN since the end of last year, so not so long, and I work in a section called BECEM MRO. And here MRO stands for Mechatronics, Robotics and Operations. So exactly like the title says, this is pretty much what we do. But before I get to the details, perhaps I'll give you an introduction to CERN in general. So CERN I like to think of as the largest machine on Earth. At CERN, the principal mission is to do fundamental research in the area of particle physics, really trying to understand what the universe is made of, how it came about in principle, and then to also understand new materials and new interactions between particles. And this is undertaken via different accelerator rings in our accelerator complex. So we're located on the French and Swiss border in Europe. And here you can see the border itself. We have two main sites, one in France and one in Switzerland. And then these, you can start to see the two injector rings that then feed into the LHC. So the LHC is the Large Hadron Collider. This is the very big yellow circle that you can see on the screen. This is a 27-kilometer long accelerator ring, where basically we speed up particles and then smash them into each other to break them into smaller pieces and see the energies that are created. So collisions take place in these four main experimental halls, and some of them you may have heard of because India is quite active in many of these experiments. And just these are, say, some beautiful, I would think, images of the different experimental setups. So we have Atlas, Alice, CMS, LHCb. But I also wanted to tell you that they are maybe the images that you see in the public, but there is so much more underlying all of these experiments for everything to actually work day by day. So to give you an idea, many people sometimes ask me, what do you actually do? I mean, what do you do in your normal day of work? So I thought I'd take you through a brief day where I go into the tunnels. And it's not every day that I'm going into the tunnels, but it's quite often, especially in this period, because we are in something called a long shutdown. And a long shutdown is where there's no beam for potentially 3-4 years. And in this time, we do a lot of maintenance, a lot of repairs, replacements, upgrades, et cetera, et cetera. So this is the time where it's very busy inside the tunnels because we are making sure that all the equipment is working as expected. And we in our group are responsible for mechatronics equipment. So these are often things that move inside the beam. They might be detectors or devices that can clean the beam. And so we're responsible for the controls and the actuation. But we also use robots to run many different tasks inside the accelerator complex, which I'll come to later. So just an example of what the day might be, you collect the equipment you have to take into the tunnel, you drive to the point of access where you're actually going, which can be many kilometers away. In the first video, you just saw some mountains in the background of the site in Switzerland and France. It's really a beautiful area. Then, of course, when you go into the tunnel, you need to prepare all your safety gear. So you have protective clothing, steel cap boots, dosimeters to measure any radiation around you, sometimes an oxygen sensor to make sure that there's enough oxygen to safely breathe, of course, a hard helmet, and in these times of COVID, a mask. And then you go through the access gates to get into the tunnel. You take the lift down. The LHC is about 100 meters underground, so it's quite a long lift. You walk to where you're going. In this case, this was a project to install some components at what's called the beam dump. So in the LHC, there are two beam dumps, which is when the particle has finished accelerating, they will then potentially, well, when needed, dump the beam into a large block of shielded graphite, which you can see in the right photo. And then the task really depends on what we're doing. So it might be installation of electronics, checking signals, checking sensors, performing calibration. And of course, a lot of my work is also project management, meetings, checking things are on track, coordinating with different sections around CERN. Because the great thing about mechatronics and robotics, because it's so cross-disciplinary, you interact really with a lot of different groups. So what I've learned since I started working here is that CERN is breathtaking in its complexity. It's the largest machine on Earth, but I would say it's also one of the most complex, simply because of the level of integration required for all the different components to work together. So I picked 3 photos. The first is what was really impressed me when I came here is all the cabling. There are thousands of kilometers of cables going from surface to ground, underground, between different areas, and keeping everything together is really an act of magic. And then I wanted to show you some of the devices. So this device in the middle is what's called a piezo goniometer. So this device controls really at fine resolution and very, very low motion at microradian level. It controls the rotation of a crystal around the beam, and this crystal is able to clean the halo of the beam and direct the outside of the beam into another device later on. And in effect, it cleans and focuses the beams. So this is just one device among hundreds and thousands all along the beam line. So you have this complexity at the small scale of the device, but then also imagining how it all fits in together to make the whole machine work. And then CERN has been using robots for many decades. So I also wanted to show you this photo of Mantis. So this was an old teleoperated robot. This was the primary device, the device that the human operator would control. And then that device would control another robot further away. And you could have, say, reciprocating motion between the arms of the primary robot here and the secondary one not shown. So we still use this type of technology at CERN today, but just in slightly more different looking hardware. But conceptually, the situation is very similar. And we can draw parallels with also robotic interventions that we might use in space or in many other areas, for instance, underwater, in medicine, in other industrial areas. So to go a little bit more in detail specifically about our robots, at CERN we've built up different robotic platforms to do different tasks. So some platforms we research and develop and integrate ourselves here, and some platforms we buy commercially if they exist to be able to do the tasks that we need. So we have robots that run, for instance, on rails that you can see in the top left. This robot is called the Train Inspection Monorail, or TIM, and it runs in the LHC. So it runs the whole 27 kilometers around the LHC. And on this monorail, we can put different sensors or different arms, different devices to do the type of task that we need to do. And I'll give you some examples a bit later. And then we also have robots that are on tracks or are on wheels, depending on the surface that they're driving over. And generally, they're equipped with 1 or 2 arms, plus sensors, for instance, cameras, LiDAR, radiation measurement systems, to really understand the environment around them. And of course, different sizes according to the type of area that we need to access. So going first to TIM, this train inspection monorail, you can get a bird's eye view. So this is inside the LHC. We see we're going past a lot of different control racks on the entrance. We have these sector doors, which are there for safety to block different sections between access when it's not required. But TIM, the robot, can pass through all of them as needed. And here you can start to see the beam line, and it's dropping right now a sensor to measure the radiation levels so that it can go through the tunnel to understand any, say, what we call hot points, or just to make sure that the levels are safe or as expected. So we have other projects ongoing with this robot. So one of them, I'm not sure if you hear the sound of the video, but hopefully not. One of them is to measure what we call BLMs, or beam loss monitoring sensors. These are the yellow cylinders that you can see. So for this, we're building up a new wagon that goes on the TIM monorail, and it has a 9 degree of freedom arm equipped with both cameras, radiation sensors, and a radioactive source. And it scans this radioactive source along the sensor so that it triggers the sensor. And in this way, we can just check that the sensor is acting as we expect it to act. So the challenge with this particular experimental setup is that there's around 4,000 of these devices in the LHC. So you can imagine in previous long shutdowns, it's taken a long time to measure these systems manually. And because you're handling a radioactive source, there is some increased risk to the operator. So the idea behind doing it with a robotic system is that you can save the risk to the personnel so that they don't have to be in contact or close contact with a radioactive source. And potentially in the future, we can do it more quickly. So for this, we start to bring in new technologies such as machine learning for object recognition and classification, autonomous trajectory generation, so that we hope in future this is a fully autonomous system. And right now we're working at different levels of autonomy. So we will have an operator either manually controlling it or controlling it with supervised actions. So this is one of our ongoing experiments right now. There's other reasons we need robots in tunnels. For instance, often we need to understand the structural integrity of the tunnels themselves. Perhaps there's a small water leak or there's some cracks, and we'd like to monitor how those cracks are developing so that if needed, civil engineers can go in and fix up that part of the tunnel. So for this, we're exploring new camera systems. Again, a lot of machine learning behind the automatic detection of cracks and classification if they are potentially dangerous or nothing to worry about. And you can also use different types of sensors, not just, say, imaging in the optical spectrum, but also looking with other frequencies to have a better idea of what's going on. For instance, with a heat map, you could understand if there's water present or not, even if it's not so easy to see with the camera view. Because one of the challenges we find in tunnels is the lighting conditions can change really quickly or between sectors. Maybe the lights are on, but in others the lights are off or it's much darker. So the system needs to be able to adapt for that. Another experiment that we've been part of is also with the fire brigade at CERN. And this is the idea that perhaps in the case of an emergency, if you have smoke or if you have reduced visibility, you can send in a robot to try and identify if there's a person in the tunnel and if that person needs help. So we also are doing quite some research around health monitoring of people. And this has follow-on applications in other fields, for instance, in hospitals. If you would like to monitor people using sensors that are, say, remote from their body. So looking at the person, but not attached to the person. So that's moving on from Tim. We have other robotics in use at CERN. So this robot here is more of a traditional robot that you might see in assembly lines. And we use this robot to move radioactive sources in and out of their storage area to the beam target. So this is an experiment called ISOLD. And these radioactive targets are probably moved around 30 times a year. So it's a very hot area. You don't want to send people in there if you don't have to. So this robot is really a useful example of quite an automated task, but still using a robotic system where we can change the trajectory if needed to adapt it to a new source. And then we have a range of, say, wheeled robots. So this wheeled robot is called CERNbot, and it's doing another RP measurement as it goes. And while it does that, in this case, we're also testing visual odometry. So based on point clouds, based on information from sensors to understand the motion of the robot platform itself, you can put all that together to build up a map of your environment and understand where you are. So in some accelerator tunnels, like the LHC, we have quite a good idea of where we are. It's a well-known environment. But in other tunnels or, say, connection points, which might be decades old, often we don't have these exact up-to-date maps. So in this case, it's really useful to have some intelligence on the robot so it can do these mapping and localization tasks as it goes. And this is a robot called the Charm robot. It's a much smaller robot equipped with a camera. And it has also special access doors, so it can go in, the operator can check what is going on and see, again, mostly in areas where there's some radiation, so you would prefer not to send a human in. So for the sort of inspection tasks that it can do, it's very nice to have robots that can be easily used to do this. But it's not just the hardware that we build up and the control systems, but we also do quite some work around simulation. So the idea is that if a inspection, maintenance, or repair task can be done remotely using a robot instead, it's often an advantage to send a robot, either because it's safer for the operator, or it can be faster, or the robot can perform a task in a way that a human can't. For instance, you can have multiple arms coming from the surface more easily than you could have a human accessing this point. So we will, of course, simulate the intervention if it's complicated before we do it, to understand the access, what sensors we need, what tools we need, if we need to make new tools, and then perform the intervention itself. So maybe a little bit around my background, how did I get here? Because it's a very interesting role that I'm in, and often I think perhaps people don't, maybe they don't know about CERN. Perhaps in this audience you've heard about CERN because you are obviously interested in science and engineering. But if you do know about CERN, maybe you think of it much more as a particle research, a physics research center. But it's also really an area where there's a lot of technical development, research, cutting edge, novel integration of new technology. It's a really interesting place to work. And this is why I wanted to share to you today what we do with robotics and mechatronics. I'll come to the space related aspect, but also to get you excited about potentially working in this field, in robotics in general, but to think also that combining technical advancements with fundamental research at a place like CERN is a really fantastic opportunity to develop your career. So my background is really in mechatronics engineering. I studied an engineering degree originally in Australia, and then I came and I did a European master's called the Erasmus Mundus program. This is also open to international students, so it's interesting to look up. It's a 2-year master's program, and I was based in France and Poland. So my undergraduate degree was mechatronics in general, and I had a space flavor. So we studied typical space subjects like orbital dynamics, understanding rocket equations, fuel requirements, some materials engineering. And then but the main program was supposed to focus on mechatronics. So this was a third electrical, a third control, and a third mechanical, to put it like that. My master's degree was much more focused on robotics only. And then I recently completed a PhD. So my PhD was in the field of surgical robots, which you may not think is related so much to CERN, which is more based around inspection robotics, or something like space, which is based around, well, it depends on the field, but say the typical examples of robots in space you would imagine are rovers, or arms, for instance, on the International Space Station, or arms on other rovers. You could also think potentially of a satellite system as almost a robot, in that it has some intelligence, it can move, it has many sensors. So these applications you would imagine in space. But also in medicine, the same use of robots can be quite interesting. So for all of these cases, you want to have your operator, your expert, being able to control a robot that might be physically separated you by a very far distance, like in space, or it might be physically separated from you because you want to send it somewhere dangerous, or somewhere where it might be a little unsafe for a human to go, like a radioactive area at CERN. Or potentially you would like to have your robot placed at a place that is maybe inaccessible or hard to reach for a human. And this can be true in medicine. So we can use teleoperated medical systems, for instance, for remote medicine. You can have your expert doctor located somewhere central, but they could have these robots that they can control in many different places. And in this way, you can share the expertise more easily of that doctor. Or, which is more the area I was working on, you can make robots that are very small, or you can make robots that can do tasks that a human just can't do, either with their fingers or with tools held by them in their hands. So for instance, my surgical robotic PhD was around the development of a needle or a catheter that was soft and steerable. And this was aimed at neurosurgery. So that, for instance, in the case of people that may have, sadly, a very aggressive type of brain cancer, if you can't operate because it's not close to the surface, or to reach the tumor is, say, very risky for the surrounding areas of the brain, it can be useful to send in a needle to avoid the regions that you don't want to touch, but accurately reach the tumor, for instance, to deliver drug therapy. And this was the motivation for our research project in this field. So we had this catheter, this needle that you could control to steer through the brain and accurately reach the point you wanted to go. And the nice thing about this is that the challenges of robust control, of reliable operation when you might have, say, some delay in your communication or some packet loss of information, good user interfaces so that the doctor could easily understand what was going on and learn the system, as well as the integration of for instance, artificial intelligence, or at least some machine intelligence, so that you have some extra sensors that help the operator, or in this case, the doctor, know where not to go or where to go. So these are some of the parallels that robotics has in all these applications. You need good interfaces for your operator, and you need, say, a safe and reliable connection with your robot. And of course, your robot needs to have the capabilities to do the task at hand. So that was my education, and based on my work experience, well, I was lucky to be able to do internships both in Australia and in Europe. And I would highly recommend, if you have the opportunity to take up an internship, you do, because you learn a lot and you see how other people work, which can be very useful. And generally, I would say you become part of a team. And in robotics, the team is key, because a robotic system is complicated. You need people that have different backgrounds and different approaches in order to create an integrated system that works. So after I finished my master's, I also had the opportunity to work at the European Space Agency, or ESA, for about 2.5 years. And at ESA, I was working in what was then called the Telerobotics and Haptics Lab, now the Human Factors Lab. And we were building up robotic systems to control robots over a large distance with some time delay. So in our case, we had different experiments going on. But the main experiment we had was under this program or project umbrella called Meteron. And Meteron really wanted to understand how we could teleoperate robots safely when you had delays in your communication. And simply in this case, because of distance between, your point of sending the signal and receiving the signal, as well as loss in your communications line. And we also wanted to understand the say, effects of haptic feedback. And haptic feedback is the sense of touch. So normally when you control a robot, you can see what the robot sees, perhaps from the feedback from a camera or from other sensors. But it can be really useful to also feel what the robot feels, because this can allow you to do tasks that require delicate manipulation. Or haptic feedback can also be used as a way to improve safety, so that if there's a region that the robot shouldn't go in, you can feel that in your primary device before you make the robot go there. These sort of boundaries of force. So at ESA, we had sent a haptic joystick, a 1 degree of freedom joystick, that an astronaut could use in space to control robots on the ground. And with this joystick, we did a few different experiments. First, we just were trying to understand how an astronaut feels haptic feedback, because of course, say there's no gravity in space. So how you feel force is quite different to how we expected to feel force in space is quite different to how you would feel it on the ground. So they were some of the early experiments to understand if, for instance, astronauts could discern different levels of stiffness as well as they could in space or on the ground, or if they could do tasks that required haptic manipulation as well as they could in space than on the ground. And I'll show you a video just in a minute of, say, the culmination of this project, which was the Interact experiment. And then I also had the opportunity to work after my PhD, and in part in parallel with my PhD in London, as a project manager in a European project called DIH Hero, or a Digital Innovation Hub of Healthcare Robotics. And for this hub was a European Union project that aims to improve the uptake and trust and collaboration of commercial healthcare robotic systems. So really, it's the idea to bring this whole industry up, which sometimes there are some very big established players in this field, but there's many other, say, startups or small companies that are still growing. And I think as robotic systems are used more and more in healthcare applications, people see that they can be useful and they start to trust them more. And it's taken a long time to get here, because with any new technology, I mean, not so new now, robotics has been around for, I would say, 40, 50 years. But the increases in the abilities of what you can do with robotics has really jumped the last 20 years. And in healthcare, this is really important because the system, whatever system you use, has to be 100% reliable and safe. And it was really interesting to be part of this healthcare robotics network as a project manager, because I was able to see a different aspect of both working in a team and running a team, and also a different side to developing robotic products. So moving a little bit more from the research into the application fields. So this is a video from Interact at ESA. Do you hear the music from the video?
Nope.
Okay, good. Sorry, it's a little distracting in my headphone. So the idea with this experiment is that we had an astronaut, in this case, Andreas Mogensen, Danish astronaut on the ISS, controlling Interact, which was the name of this robotic rover. And the task that he had to do was drive around a simulated moon. In this case, this was our site at ESA on the ground, but they were in space, to find this taskbot and put a peg in a hole. And that might sound quite easy. Let's see if I can play the video again. But the tolerance of this peg to the hole was very, very small. So to put the peg in the hole just by sight is really hard. It's a bit like if you have very cold hands and you're trying to put a key into a lock. If you can't feel what you're doing, it takes you much longer to pop it in. But if you can feel what you're doing, that haptic feedback, you can very easily pop the key in the hole. Okay, maybe not the perfect analogy here. So when the astronaut lined up this peg with the hole, he then had haptic feedback in his joystick to feel if there was any misalignment so that he could then come out, try again, and go in again. And he was able to successfully do this with a time delay of around 800 milliseconds. So that's almost 1 second of time delay. And if any of you have studied some control theory in your courses or perhaps in your workplace, this sort of time delay means that either you have a system that's very unresponsive. I mean, you do an action, you wait a second to make sure that that action is done, another second to see the feedback, then you do the next action. Or you have really some intelligent control system running on the robot that can mitigate that time delay so that you can have relatively smooth motion that doesn't oscillate, that is stable as well. Because that's also a factor when you have haptic feedback, is that you can introduce these oscillations in your systems. So for this experiment, it was really a nice culmination of a lot of research and development from the whole team so that we could successfully do this operation from space with such a time delay to show that actually operators, astronauts, controlling robots over large distances with haptic feedback is really feasible. And maybe this is not so relevant right now, but when we start to have more applications on, say, the moon or potentially Mars, if we need to build up habitats, this type of complex task, this is where it will be very useful to send robots to at least do the base work, but still have the intelligence and the reaction of the human operators in that control loop to do the task. Some people say that teleoperation is simply a step towards autonomy, and in many cases it is, but still having the human in the control loop for many cases can just be completely necessary to ensure either safety or the correct action is taken. Perhaps that changes in the future. And the other sort of area of my background I wanted to highlight, because I think many of you are doing similar things, of course, with Infiniscope, it's a fantastic example. It's just community involvement and this sharing of knowledge, sharing of enthusiasm, sharing of motivation actually for the research or the work that you do. And space is one of these fantastic communities where everyone that is involved is so motivated and so passionate about what they do. And it just creates this environment where you can very easily share connections, share knowledge, and say grow both your personal development and your career development that way. So whenever I've had the opportunity, I've gone to many talks about space, robotics, science, and technology in general. And I've really enjoyed being part of communities such as Women in Technology, which is at CERN, and this was the initial connection to Infiniscope. And there's another community I wanted to highlight, which is called the Space Generation Advisory Council. And this is an international not-for-profit organization that aims to give a voice to people interested or working or studying in the field of space under the age of 35. So they're connected with the UN COPUOS Committee, the Committee of the Peaceful Uses of Outer Space. And they run different events all around the world. There'll be an SGAC India group, for instance. And they're just, I would highly recommend, if you like space and you don't already know about SGAC, it's worth connecting to them. So just to end with, I wanted to briefly talk about the areas of technology that I think are growing and the areas of technology that, say, have to be integrated well for a robotic system to work, no matter the application. Application can be in space, it can be at CERN, it can be in industry, in a medical field, anywhere. So the first is human-machine interfaces. So for teleoperation, to have this interface that the operator can easily understand, that they can easily change and manipulate is really important. And the future of this technology seems to be going towards augmented reality, virtual reality, showing the operator more than what they could just see with a view of a camera. And this can increase the immersion. It can increase the experience that you're right there with the robot. And hopefully, I mean, the aim, of course, is that the task is easier to do, or you can do the task more safely or faster, however it may be. And so at CERN, we have research going on in creating, say, the new generation of interfaces to control our robots. And there's a little photo on the left where you can see, for instance, part of the LHC in simulation. And in this case, the idea is that if we can have cameras or point cloud sensors, for instance, in the tunnel on a robot, we can mesh that point cloud or mesh all of that information with the 3D model that we already have of the environment. And then you can really, you can operate anywhere you want in that environment because you would understand intrinsically where everything is. I'm not explaining that so well, and I don't have a video to show you, but I just meant to say that new sensors, new imagery, and new methods of showing information to the user can mean that soon these human-machine interfaces are really excellent to use for the operator. And hopefully then non-expert operators can control these robots from anywhere to do complex tasks. Of course, for this to happen, we need the appropriate hardware, the appropriate tools, so the end effectors, the type of arms that we have. So this, I think, fundamentally comes down to development of new electronics and new actuators, perhaps not just motors, pneumatics, hydraulics, but perhaps moving towards more compliant systems or softer arms, things like this. It really depends on the task. And then, of course, pulling that into this field of teleoperation and haptic feedback. So having reliable links, safe operation, robust control with appropriate sensory feedback. And not just this, there's also a lot of software development that has to be done. So computer vision is really useful. I mean, traditional computer vision, I think, is a fairly well understood field now, but it's still growing in terms of the algorithms that we have to detect different objects, understand them based on shape or texture or color, this sort of thing. Machine learning, again, perhaps in connection with traditional computer vision techniques, but to classify objects, first detect objects, then to classify them, so that the robot can understand what is around them in the environment without the human telling them. New methods of teaching robots. So one that is often spoken about is, say, learning by demonstration. You show a robot how to do a task in reality or in simulation, and then the robot can learn itself based on, say, machine learning techniques or reinforced learning, how to do that task successfully. And of course, new sensors. So this comes a bit back to the hardware, but we're seeing that now on the market, we can have really affordable, for instance, LiDARs, and in a small package. So which means that we can put these on robots much more easily than we could in the past. And I would say driving this field of development are electronics in our smartphones, because things are getting smaller and cheaper at mass manufacturing, as well as fields like autonomous driving, which is pushing these sensors to become more reliable, more accessible, and easy to integrate into systems. So I'm almost at the end. I just wanted to highlight something relatively new, but perhaps you know, but India actually became an associate member of CERN at the beginning of 2017. The collaboration and the partnership between CERN and India goes back much longer, actually, decades. They were part of the construction of the LHC, and they've contributed to both the CMS and ATLAS experiments. But now becoming an associate member of CERN means that people with Indian nationality are eligible to apply for many different roles at CERN. So this can anything from internships to longer contracts, such as a fellow, even potentially for staff roles if the associate membership changes in the future. So I highly recommend you, if you're interested in working at CERN one day, check out the different roles that come up. So it's every, say, twice a year that there'll be an intake of applications, and then that feeds into a pool. And then anyone at CERN that has a position open can see those pool of applications. So it's quite a useful way to to show your experience and your CV and your background to everyone at CERN at the same time. And finally, a big thank you to Kirby and to Infiniscope for inviting me here and for putting it together, and actually just for doing the mission that you're doing. So you want to bring space to everyone, and one of CERN's missions is to bring a global involvement of science and technology and a global collaboration. And I think really these motivations, these aims are well aligned to share scientific knowledge, but also share, say, excitement and passion in this field.